Okay. There we go. So just to review this for the record, this is what the final is going to be like. And I forgot that I did something different here. I'm not going to do something. Neither one of my calculus finals are going to be aligned due to this proctored situation. So I'm going to need from each one of you the email of a proctor, right? If you are still in town, you're welcome to take it at the Edge Center, okay? If you're still in town. So just for the record, you'll be gone. Will you be here? So you'll be at Edge. Perfect. So, yeah, there won't be any time restrictions. What I do want, though, is I would like this sent it photographed and sent back to me that evening sometime. Okay. And so, Elizabeth, are you going to be here next week, or are you going to be in somewhere else?
I'll still be in isolation. That's what I wanted to talk to you about.
So next Thursday, you'll still be in isolation.
Yes, but I get out like the day after, and then I'm going home. So I was going to ask if maybe I could take it when I got home.
All right. All right. Well, give me the email of someone who can proctor that, okay, to whom I can send the exam with some instructions, okay?
Okay.
It could be any trusted person, but I don't want somebody that's going to. I want somebody that's going to, be able to follow some instructions. Mainly, I'm thinking of a parent, a minister, somebody like that, right?
Okay.
Something like that. So you and Brianna are in that situation. All right. Yeah, okay, that's what we'll do. So this is their responsibilities. This is in the notes. They have to print the test, monitor it, photograph the completed test, destroy the paper test afterward, and provide me their email. That is the first part, right? Uh-oh. Look at that. You have to provide me their email. That's you. Okay. After talking to them about it, I don't want to be sending stuff out there. Why is this? Okay. All right. So. Where are we at here? Okay. We're about to do some integration using exponents or exponential functions, and the these are the integration rules up top. We're just going to jump down here and start looking. Actually, probably B is a little easier than A. But here's what we're looking for. We're looking for e to a power times the derivative of the power. So this is the form. We'd like e to some power. And then down here, we need power prime, the derivative of the power, okay, in front. That's the format. That's that format, okay? So, let's do part A first. Here we have x times e to the x squared. So we have e to a power. What is the derivative of the power? So we could go over here and go, okay, let u equal x squared. Du is 2x dx. All right. Now I'm substituting in. So if I go to substitute in here, I want to get integral e to the x squared is e to the u. Then what is x dx? X dx is 1/2 du. And so that's going to be a 1/2, put that way out here, and then du. All right. Well, that equals 1/2 e to the u. According to this up here at the top, right? U is x squared. That's going to be 1/2 e to the x squared plus c. So when you take a derivative of e to some function, you just take the derivative of the function and put it up front. You take the derivative of the power, and it goes up front when you're taking a derivative. When you're taking the antiderivative, you need the derivative of the power somehow up front, and it goes back up. It's the opposite. So down here, part B, we're going to do a little different. I could ask this very simply. If this were my u, what's du? Du is 3 dx. Well, I have a dx, I don't have a 3. So this is going to look like this. Integral e to the 3x plus 4 dx. So I stick a 3 there, and a 1/3 out here. So now I'm using it, I'm doing this quote unquote my way. Right? Where now the derivative of what's up in the top is now up front. Well, that integrates to 1/3 e to the 3x plus 4 plus c. Things get more interesting. Things get more interesting. E to the cosine 2 theta. Well, here's e to some power. This looks something like close to the derivative of that up there. Okay? Close. So we're going to have a pop quiz. We're going to make this bu, right? So over here, let u is cosine 2 theta. Pop quiz, du equals, fill in the blank. Chain rule. On your paper, put down the derivative of cosine 2 theta. Okay? That is derivative of cosine is negative sine. So I would have a minus sine 2 theta. But when I take the derivative of cosine, this 2 comes out. Now, when I do these pop quizzes, I don't go around and say, did you get it right? Did you get it right? Did you get it right? Right? The idea is, if you didn't get it right, you're going, better go back and look at those. Right? I'm hoping you're that self-aware that you're doing that. So what do we have? I got sorry, one last thing here. D theta. So I have sine 2 theta d theta. So sine 2 theta d theta is going to be 1/2 minus 1/2 du. And so I don't quite have, this needs to be a 1/2 du. So this is going to be minus 1/2 out front, integral e to the u du. So those who like doing the substitution, they go over here and it's clear what they need to be looking for outside of the exponent, down in front. That makes it clear what has to be down front for this to work. And so what you needed was a -1/2. So if I were doing it quote unquote my way, I would have stuck in a -1/2. No, sorry, check that. I would have stuck in a -2 here and -1/2 out here. Don't write that on your paper in addition to that. But that's the way I would have started using quote unquote my way. Right? By the way, it's not my way. It's a lot older. It's older than even I am. All right. So this is going to be -1/2 e to the u, but u is cosine theta. That's -1/2 e to the cosine. Did I say cosine theta? I meant cosine 2 theta plus c. These next two. Part D. Where do you even begin? Well, up here, I had e to a power, and I had some stuff up front that looks like it could be made into the derivative of the power. In part D, I have e to a power, and I got nothing up front, much less having something up front that could be made into the derivative of the power. What do? Don't panic. But now's a perfectly good time to panic. That's my best Dorothy in Wizard of Oz. Let me ask you this. What would be the derivative of that? The derivative of e to the t plus 1, well, the derivative of e to the t is e to the t, the derivative of t is 1. But I don't have an e to the t up front. I don't have an e to the t plus 1 up front. So when you see something like this, this is something you're just going to have to put on your toolkit. And by the way, down in this one, toolkit as well. Okay. Write this as that exponent. When you have the same base, the way you combine them is you add the exponents together. So when you add these two exponents together here, you get the e to the t plus t. Now ask yourself a question. I got e to the t. What's the derivative of up top? I want the derivative of that power down front. Well, the derivative, I got e to the t. The derivative of the power, e to the t, is e to the t. We just happen to have one laying around now. So let's go over here and say let what? U be e to the t. So du is e to the t dt. So this part is u, this part is du. And so that's going to equal integral e to the u du, which integrates to e to the u. But u is e to the t. E to the t plus c. Yeah. So don't be afraid to break up the exponent into this product and you may have e to something and then the derivative of the something. Keep that in mind. Stop me with questions. So far, students have told me, by the way, they like the camera further away, so I'm going to keep it that way, further away from the board. As you can see when I point to something, right? But you see the board on most of your screen. So, this guy, part E. I want e to something times the derivative of the something. But I don't have that here. I have e to the x, and then it's divided by this stuff. But it's important, once you're in this section doing all these exponential derivatives or exponential derivatives and antiderivatives, that you don't forget the rest of your calculus. That numerator looks suspiciously like a derivative of the denominator. So over here, let u equal 1 plus e to the x. Du is then e to the x dx. And so this stuff becomes du, well, this is u. And up here, that is du. All right? Now, I'm doing a substitution. Keep in mind that this is x equals 0 to x equal 1. All right? I'm seeing a little bit, well, this will be interesting. Now, you remember you have two different options. We're going to convert this. This is going to be integral. This is now du over u. Question. What do I do with these exponents? Well, we have two choices. One, we can convert them to u's. Or two, once we get this derivative, antiderivative, we can convert it back to x's. Because these are x values here. So you have choice. Convert them now to u's, and then never see x again. Or take the antiderivative, and then convert it back, the antiderivative back to x's, and plug in the original values. Take your pick. Let's convert them. If x equals 0, then u equals 1 plus e to the 0 is 1 plus 1 equals 2. So this bottom bound is 2. So 0 doesn't always go to 0. Don't get into that trap, right? Then we have x equal 1. So u is going to be 1 plus e to the 1, which is just 1 plus e. Now that's a strange bound of integration, but 1 plus e is just some number. E is 2.72 and change. 1 plus e is 3.72 and change. So up here, we put 1 plus e. So we're going to have du divided by u integrates to natural log of the absolute value of u. bounds from 2 to 1 plus e. That equals natural log of 1 plus e minus natural log of 2. How come I can lift the absolute value signs? What happened to these absolute value signs? Well, 1 plus e is 3.72. That's positive, right? So you can lift, you can remove absolute value signs when you know the value of what's inside. Excuse me, the sign of what's inside. So I know that 1 plus e is positive, so I don't need absolute value signs. I know that 2 is positive, so I don't need absolute value signs. So that is a little bit of a strange answer, but that is our answer. Questions on that? So these last two involve a little bit of chicanery, right? It gets a lot worse than that. We're not going to go too far there. Homework from book. Why didn't I put homework there? Well, that was something that slipped through the cracks. I should have put some homework there, which means you will go into the section and find some homework, okay? But I mean, I should have put homework there. Bases other than E and other applications. So now, up to now, we were doing e to the x. Well, what about 3 to the x? What about 3 to the x? Right? Okay. Now, you may not be convinced of this. A to the x is defined by that. You may not be convinced of that. Wait a minute. We have a property of logarithms. That log to any base, but I'm going to do natural log of m to the n power is n natural log of m. That's one property of logarithms. All right? So to convince you of this relationship right here, this is the key relationship. To convince you of that relationship, let's look at the right-hand side. E to natural log a. What is that? That's going to equal e to the natural log e to the natural log of a to the x. Okay. Question. What is e to the natural log of anything? E to the natural log of star. E and natural log are inverse functions. E to the x and natural log x are inverse functions. Put a different way, natural log of star is the power to which you must raise the base of natural log, e. So this is the power to which you must raise e in order to get star. Natural log of star equals the power to which you must raise e to get star. But I'm raising e to that power. So I'm raising e to the power to which you must raise e to get star. This had better be star. So here I have e to log of a to the x. So this is e raised to the power to which I must raise e to get a to the x. Let me say that again a different way. Natural log of a to the x is the power that I have to raise the base e to get a to the x. But I'm raising e to that power. So that equals a to the x. So this right here is an identity. This isn't any, mumbo jumbo going on here, right? However, that identity gives us some power. Because what we're going to do next is take that identity and do d dx of a to the x, and then d dx of now remember that a is, if a is 1, you have a very simple relationship. It's a constant function. So here a is different. A is assumed to be different than 1. If you don't, you have e to the 0 and you're okay. But it's positive. So natural log of a is just some number. Natural log of a is just some number. Now, how do you take the derivative of e to the anything? You take the derivative of the anything, put it down in front. You take the derivative of the, so the derivative of this exponent, the derivative of that is, the derivative of that with respect to x is just log a. Natural log of a times e to the natural log of a x. You take the derivative of the exponent and bring it down in front. So picture log a is just some number in front of x. If this were e to the 3x, you'd bring a 3 down in front. It's e to the natural log of a x, so you bring natural log of a down in front. Now one more little thing, and we have enlightenment. Hopefully it's enlightenment. What does this equal? That equals a to the x. So this equals natural log of a. This whole thing in yellow just equals a to the x. So the derivative of a to the x with respect to x is log a to the x. Now, just as a quick one, don't write this down. But if this were an e, this would be an e, and that would be an e. But log base e of e is 1. This would be a 1, and so that turns into the derivative of e to the x is e to the x, which is what we just had. Now, if we have it to any other base besides e, that's positive and greater than 0. No, positive and not equal to 1. This is our formula for a derivative. That's our formula for a derivative. So the next page, right? Actually, we have, here we go. Coming up here, we just proved this relationship here. Okay. We just did a little derivation of that. It wasn't real hard. But let's go back to the next slide. All right. Definition of a logarithmic function to base a. They're making this too hard. This is what's in the book. But log function base a, remember, log base a of x equals the power to which a must be raised to equal x. That's what log base A of x is. Here's the way they're defining log base A of x in symbols. Now, if you understand logs, the symbols make sense. But logs tend to be a little bit rusty, right? So in my humble opinion, keep in mind this definition here. The log base A of any number is the power to which A must be raised to equal that number. Now, where does this come from? Where does that come from? It comes from the change of base formula. Oh my gosh. Right? And that's over here in the bottom right. Oh dear. Log base A of x. If you have log base A of x and log base B of x, this is a formula. Log base A of x is log base B of x divided by log base A. That's a property of logs. So over here on this on our calculator, you notice on your calculator, you have two log buttons, LOG, base 10, and natural log, base E. You only need one. You only need one because if you have one, you can get the other one. And this is sort of a proof of that, right? This right here, if I wanted to take, for example, looks like I erased something here. I think there was an example here. It got erased. Example. Log base 7 of 45. What is that? That got erased. So add that in. Well, using the change of base formula, that equals. Now you want to change it to a base that you have a way of calculating. So we have ways of calculating log base E, log base 10. So take your pick. Let's do log base 10. This will be log base 10, which we never write, of 45, all right, over log base 10 of 7. And on the calculator, you see that comes out to about 1.96. Right here. And then to check our answer, we claim this is the power to which I must raise 7 to equal 45. If on the calculator I raise 7 to that power, I do get 45. Now we don't have a log base 7 key on our calculator. So this change of base formula comes in handy. You come up with these change of bases, not as much as you used to, but you come up with them as still a fair amount in the natural sciences. Okay. Similarly, we could have used, here we use log base 10. This also equals log base E, natural log of 45, divided by natural log of 7. That also equals around 1.96. And that's the bottom screen. Right? That's the bottom screen. Right? Doesn't matter how you do it. But this has got to be something you have, especially if you're going into the natural sciences.
So is this going to be on our test?
Could be, but you'll have, if it's online, yeah, this could be, yeah.
Is this?
Oh, time out. Yeah. Oh, I know where you're going. I will not require you to do anything that requires a calculator. So you could leave your answer like this.
So is this kind of stuff that would be on the final test, not like the final, but like the last one that we take?
Yeah, it could be, but if yeah, the one next week.
It would be the one next week?
Yeah.
Okay.
Now we have some issues here because with on this thing, well, it's going to be supervised, and I don't usually So that's where the monitoring takes place. You're not going to have your calculator on the final. I'll say that right away. But you could leave. If I said to convert log base one thing to log base another, you can just leave it like that, circle. You don't have to. I'll never require you to come up with 1.96 on your. I can't do it. Right? If I can't do it, there's a lot I can't do. These are some properties of inverse functions. I've already mentioned them. Right? This is the one I've been using all along. That x is the power I have to raise the base to get what I'm taking the log of. So x equal log base a of y means that a to the x power equals y. And then these two just means they're inverse functions. I said this a second ago. This is log base a of x is the power I have to raise a to get x. If I raise a to that power, I get x. And then similarly, this is what power do I have to raise a to get a to the x? Because this thing here is the power I have to raise a to get a to the x. Well, the power I have to raise a to get a to the x is x. So those are very basic. Those are basic. This is the last couple slides hasn't even been calculus. This is not calculus. That's not calculus. It's algebra that we probably are rusty in, but it's not calculus. Okay, this is calculus. All right, you ready? We should think for a second, because this gets a little bit, okay. All right. Look here. The derivative of a exponential is the log of the base times the exponential. Yeah. Now this is that one we already had derived in the other page. That's why that's circled. This is the one, the next one, number 3 there, is one that is often missed. The derivative of a log to base a of something is 1 over log base a times, oh, now, if this were dx, right, natural log of x, that would just be 1 over x, right? That would just be 1 over x. We've already had that. So, watch. ddx of log base a of x is what? Well, log base a of x, we have a change of base formula. The formula on the last page. Log base a of x is, it's going to be ddx of, say, natural log of x divided by natural log of a. And here's a key. Here's a key. You ready for the key? Well, that's sort of the key. But log a is a constant. Doesn't have an x in it. So that can come all the way out. So this equals 1 over log of a, and then dx of natural log of x. Well, what is the derivative of natural log of x? 1 over x. Which is this? Right? That is the same as that. Okay. Good news, bad news. Good news, bad news is a lot of these you got to either remember the formula, or remember how to get them. So, like for example, if instead, let's look at this thing circled in purple. If it, instead of a to the x, it were a to the u, then the derivative of the u would pop out. And that's what happens over here. You get log a to the u, then the derivative of the u pops out. So this on the right is the chain rule applied to the stuff on the left. Here, if I have natural log base a of u, the derivative of u pops out over here. All right. A lot of symbols there. A lot of symbols there. So if you're foggy, you're probably about right. Don't let that panic. I'll tell you, let me tell you when to panic. Panic when you haven't put graphite to paper and done a bunch of these. Then panic. Oh no, I got the test coming up and I haven't touched them. Oh, I saw them in class, they weren't too bad. Then that's the time to panic. All right? Differentiate the following. Why is that on 2 lines? Why did I put the following here? Why isn't the following following? That bugs me. What happened there? Oh, that's much better. Now, can you change that on your paper? The derivative of 2 to the x. If it was the derivative of e to the x, it'd be e to the x. But the derivative of 2 to the x is going to be 2 to the x times natural log of 2. That's this formula right here, formula number 1. This is going to illustrate formula number 2. Because I don't have just 2 to the x, I got 2 to the u. Right? Now, I'm not going to even attempt to do differentiation by substitution. Okay? But that's, to me, going way too far. But the this thing up top, picture this as a u. So the derivative is going to be, by formula number 2 up there, it's going to be natural log of 2 times 2 to the x squared times the derivative of x squared is 2x. Right? Well, you probably write that a little bit different. You probably write that as a 2x, natural log of x, 2 to the x squared. That would look all right. You may see this on a, if you use one of the websites, one of the Wolfram Alphas or something like that, you may see this written a different way. Notice I have a 2 up front and I have a base 2 here. That would be fine with me with circle, which is in the box. But this could also equal x, natural log of x, 2 to the x squared, and then this 2 that was up front, 2 times 2 to the x squared is 2 to the x squared plus 1. Yeah. So some of these symbol lab and things like that, they may combine it even further, right? Oh dear. Sine of log 2x. Oh. Well, what's the derivative of sine? Cosine. So picture this as a u. And so I'm going to have the derivative of sine u is sine of the same u. Did I say sine? Cosine. Cosine of the same thing. We have a We got a crash. Let's pray that I only lost this, what's on this board here. Yeah. And count one. Now let's go down a ways. Where are we at? We're down some more. Here. Oh, didn't lose anything. Of course, when there's only like a little bit up there, you don't lose anything. When it's the whole page, you lose it. So this is going to be cosine of log of 2x. Then the derivative of this comes out. Chain rule, right? So what's the derivative of log 2x? It's the derivative of derivative of 2x, 2 divided by 2x. And then these guys cancel. And we'll probably write this at the end. 1 over x cosine natural log 2x. By the way, don't put plus c. You only put plus c when you're finding an antiderivative, which is a antiderivative meaning without the bounds of integration. All right. d dt, sine of t, sine to the teeth. Sine to the teeth. So sine t to the teeth power. Right? That would be sine t to the tooth power. Yeah. Okay, that's bad. What do you do? We have to pull out something we did weeks ago. Weeks ago. Don't do this. Don't take the t down front and subtract 1 from the t. No, doesn't work that way. Not when it's a variable up there. All right, what we're going to do is we're going to do I think it was called logarithmic differentiation. What is that? Let's let this thing equal y. That's what I'm looking for. I'm looking for y. Okay? So let's consider natural log of y. That's going to equal natural log sine t. Fair enough? Natural log of both sides. We're going to use some properties of logs. So I'm going to put in an extra step here. This right side equals natural log, bracket, parenthesis, sine t to the t. Right? This thing, this t can come down front. So that can come down front. That equals t natural log sine t. All right? And I'm just for completeness, I'm going to write natural log y. Now I'm going to differentiate both sides. D dx of the left, natural log of y, equals d dx of the right. Okay? The left. What is the derivative of natural log of y? That's y prime divided by y. What's the derivative of t natural log sine t? Product rule, chain rule. I have t times another function of t, so we're going to apply the product rule here, but that's going to require the chain rule. So first is t times the derivative of the second. So t, let me put some extra step in here. The derivative of all right, first times derivative of the second plus second times the derivative of the first. The derivative of the first is just a 1. And we have a missing a parenthesis. All right. T, what's the derivative of log sine t? That's t. I'm going to put sine t in the bottom. The derivative of sine t is cosine t goes in the top. Cosine t over sine t is cotangent, right? Then this just goes along behind, right? This equals y prime divided by y. So what did I originally want? I originally wanted y prime. I originally wanted the derivative of this. So y prime is going to be y times all that stuff on the right. T, cosine over sine is cotangent t. And just not to get the t's mixed up, I'm going to put the t in parentheses. Plus natural log sine t. Almost done. All I have to do is to put y. Right? Y is that sine t to the t, right? So it's going to be y prime sine t bracket t cotangent t plus natural log sine t close bracket. And there is a really ugly derivative. Let's go back and see what we did here. I did a little bit of a misnomer here. When I said y isn't the derivative. Y prime's the derivative. Y is really this thing. This is really y, right here. Yeah. But so we took the derivative of that by the derivative of the natural log of y. We took the derivative of that. So down the left, that just stayed as y prime over y. Until the very end, we multiplied both sides by y. Then I plugged in what y equaled. On the right, we had to employ, right here, to not stand in front, because the you did bring the t down front here. That gave a product rule situation, right? So we have first times the derivative of the second is the t times the derivative of log sine t, which we did in a separate step. The second times the derivative of the first gives you this stuff out here, times the derivative of the first is 1. The derivative of what's in these brackets is the function on the bottom, its derivative in top. Derivative of sines, cosine. Then the bottom, or excuse me, on the right here, we just have log sine t. Cosine over sine went to cotangent. And it was in that stage that we multiplied both sides by this y right here. Right? So that y goes over there. Right? Y goes over there. And then we substitute in what y equals. So, yeah. That's logarithmic differentiation. Keep in mind, I just am thinking of this right now. On the final next week, you will be allowed to have a 3x5 card with whatever information you want. Right? Now, I mentioned this before, that if you've been working on this card already, you're ahead of the game. Because what you're going to put on that card is mainly things you're weak in. And so what you'll have is a weekend. No, just kidding. You're going to have a list of your weaknesses. You're going to have a list of stuff you're not quite sure about. So those are places you want to give extra emphasis in your preparation. The card is a great psychological tool, in addition to hopefully helping you on the test. Find the derivative of that buzzard there. I'll give you a hint. It's this. Use this. I probably should add a couple of more from these up here, right? So I'm going to put up here, this is for next. Note to self. That's to me, not to you. So whoever gets this next time is going to have more homework there. Because that one is not really not enough. All right. Derivatives of bases other than E. Oh dear. It's not that hard. Not that hard. We had a second ago, we looked at a slide that said this, that a to the x equaled e to the a to the x equaled e to the x times log a. Well, if I take the derivative of the left, d dx of a to the x, it's going to be the derivative of this on the right. That means I take the derivative of that exponent and bring it down front. The derivative of that exponent is log a times the same thing. But this thing just equals a to the x. All right, so now we're going to have some antiderivative action here, right here. From that formula, we get the antiderivative here. If I go in the other direction, the antiderivative of a to the x is 1 over log a, because you would divide by that instead of adding. Here, look at this function. Here, a is 5. The base, that's a. So the antiderivative is going to be 1 over natural log of a, which is just a constant. That's like 1/3. Then 5 to the x from 0 to 2. And then that's going to be what? 1 over log a. Oh, did I say log a? Sorry. Log 5. The base 5. 1 over log 5. Plug in 2, I get 5 to the 2. Plug in 0, I get 5 to the 0. So that is 25 minus 1. That's going to be 24 over natural log of 5. So what we got here next. I think we will leave it there because this one's going to take longer than we have. Now, fortunately or unfortunately, to make up for yesterday, I'm going to have to do a video to get us a little more down the road. It may not, it'll probably be a video on Thursday to make up for yesterday. But also on Thursday, we have our class time. If you, those interested, come here and we'll, during our class period, we're not going to do anything new. Right? It'll just be Q&A. Right? So we will leave it there. Bye, ladies. Bye, Elizabeth.